In our previous lecture, we learned what is independent nested loop and how to find the time complexity of independent nested loops. We learned this through an example in our last lecture. Now in this lecture, we will discuss some more examples of independent nested loops and we will learn how to find their time complexities. So let's get started and let's see the topics of this lecture. The topic of this lecture is time complexity of independent nested loops. In this topic, we will learn how to find the time complexity of different independent nested loops. We will discuss some examples in this topic. Let's take the first example of independent nested loop and let's learn how to find its time complexity. Here is the example for loop. This for loop structure is the nested for loop structure because there is at least one for loop within another for loop. We can observe these two for loops belongs to this for loop. Hence, this entire structure is the nested loop structure. Also, we can observe each loop is independent of each other. In this for loop, we are not using variable I in these statements. Variable j is independent of variable I. J is initialized to 1, not I. J is compared with n, not I. J is incremented by 1, not I. So clearly, j is independent of I. Also, k is independent of both j and I. K is initialized to 1, k is compared with n, k is incremented by 1. So these loops are independent of each other and hence we can say this entire structure is independent nested loop structure. Now our job is to determine the time complexity of this entire for loop structure. How do we do this? We already learned how to find the time complexity of independent nested loops. The time complexity of an independent nested loop is equal to the multiplication of frequency count of each loop in the nested loop structure. Here we have a total of 3 loops. We need to determine the frequency count of these loops and then we need to multiply them to find the time complexity of this entire structure. Let's first find the frequency count of this for loop. We can observe in this for loop, variable I is initialized to 1, variable I is compared with n, and I is incremented by 1 every time. The first value of I is 1, the second value of I is 2, the third value of I is 3, and so on it will continue up to n. So there are a total of n iterations of this for loop and hence this loop will run n times. Therefore, the frequency count of this for loop is n. What about the frequency count of this for loop? Here we have variable j in place of I. J is initialized to 1, j is compared with n, and j is incremented by 1 every time. This loop will also run n times because there are a total of n iterations of this for loop. Similarly, this for loop will also run n times. Only the loop variables are different in these for loops. The logic and the implementation is same. The frequency count of these for loops is n. Now we need to multiply these frequency counts in order to obtain the time complexity of this entire for loop structure. N into n into n is the multiplication of these frequency counts and this is equal to n cube. So this independent nested loop will execute n cube times and hence the time complexity is theta of n cube. Why I have mentioned theta here? Because n cube represents both the worst case and the best case performance of this independent nested loop structure. So theta of n cube is the time complexity, and theta represents both best case and worst case performance. So n cube is both the upper bound and the lower bound of this structure. So now we know the time complexity of this structure is theta of n cube. Now let's take one more example, which is a little complex compared to this example. Here is the for loop structure. Again, this nested loop structure is independent nested loop structure, and you can verify this on your own. Now, we need to find the frequency count of each for loop in order to obtain the time complexity. We multiply the frequency counts of these for loops, and this will give us the time complexity. Let's do this. Let's find out the frequency count of this for loop first. Here in this for loop, I is initialized to 3, I is compared with n, and I is updated to I cube. We know how to find the time complexity of this for loop. We learned this in one of our lectures. We learned in one of our lectures how to find the time complexity of a loop where in the update expression, the variable is raised to the power some constant. Here in this update expression, we can observe variable I is raised to the power 3, which is a constant. We know the frequency count of these type of for loops is log n, and the base of each logarithm can be obtained from the power of the variable and from the constant in the initialization statement. Here we have the constant 3 in the initialization statement, and in the power of variable I we have 3. So the frequency count of this for loop is log n base 3 log base 3. This for loop will execute log n base 3 log base 3 times. We obtained this base from this initialization statement. Here we have value 3, so 3 comes in the base of log n. And this base is obtained from this constant in the power of I. So log n base 3 log base 3 is the frequency count of this for loop, and hence the time complexity of this for loop is log n. Now let's find the frequency count of this for loop. In this for loop, variable j is initialized to n, j is compared with 1, and j is updated to j divided by 2. In the update expression, variable j is divided by a constant, and we learned in one of our lectures how to find the time complexity or the frequency count of these type of for loops. In that lecture, we learned how to find the time complexity or frequency count of the loop wherein the update expression, the variable is divided by a constant. The frequency count of these type of for loops is always log n, and the base of the logarithm can be obtained from the constant in the update expression. Here we have this constant 2 in the update expression. Therefore, the frequency count of this for loop is log n base 2. Hence, this for loop will execute log n base 2 times. Now, what about this for loop? In this for loop, variable k is initialized to 1, k is compared with n, and k is updated to k times 4. This time, in the update expression, the variable is multiplied by a constant. And we learned in one of our lectures how to find the time complexity or the frequency count of these type of for loops. We learned in that lecture how to find the time complexity of the loop wherein the update expression, the variable is multiplied by a constant. The time complexity for these type of loops is log n. Hence, the frequency count is also log n. And the base of logarithm can be obtained from the constant in the update expression. Here we have the constant 4, therefore The frequency count of this for loop is log n base 4. And hence this for loop will execute log n base 4 times. So it does not matter whether we have division or multiplication in the update expression, the time complexity is always log n. So with this, we found out what are the frequency counts of these for loops. And now we need to multiply these frequency counts. Let's forget about the bases of logarithms, because in the asymptotic notation, we will not mention these bases. Here we have log n and here also we have log n. Log n into log n is log square n. And we now need to multiply log square n by log n. So the time complexity of this entire for loop structure is theta of log square n times log n. This is the time complexity. So clearly, the time complexity of this entire independent nested loop is theta of log square n times log n. Now with these examples, I hope it is completely clear how to find the time complexity of independent nested loops. We are now done with this topic. We learned how to find the time complexity of independent nested loops through examples. So with this, we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.